and we're going to start off talking about your vehicle, if you have a vehicle. I'm sure you've ridden in vehicles before. And so all of the systems in your car are essentially wired in parallel to your battery, right? Because if, let's say, your horn goes out, you wouldn't want that in one big series circuit so that if your horn went out, the entire thing stops working, right? So you want independent branches where the current can travel, so that if one of these goes out, like if your lights go out, the engine doesn't shut off and the horn doesn't stop working and the radio doesn't stop working, because those are all wired in parallel. So one side of the devices are always connected to the same positive terminal of the battery, and then the other side of all those devices are always connected to the same negative part of the terminal of the battery. Okay, so you could have, in a system, think about how many different systems there are in a car. Think about how many fuses there are in your fuse box in your car. There could be hundreds of them, especially like, geez, I bet Tesla has a pretty interesting fuse panel, right? But anyway, all those systems run off of the same voltage, that 14-ish volts that you see. That's why I use 14 all the time in a lot of my DC circuits, just because it's a common battery for vehicles, and I realize sometimes it's like 14.3, and but anyway, so around there, okay. But anyway, they all run off the same voltage, and they all have each has their own independent current draw, okay. And so essentially, like you see here, it says there are two or more paths for the current to flow. There, in this particular circuit here, we've got 1, 2, 3 of these loads in parallel. Once you get to just two, if you just have two that are like this, so that when the current comes up to this node, it can go both this way and that way. Now you've created a parallel circuit, okay? If they're all in parallel. Now, in Chapter 7, we start combining the two, and then you have series and parallel circuits, and then, and then some students want to cry after that. But no, I'm just kidding. It's not that bad. But when you're dealing with strictly series or strictly parallel, I think those are the two most straightforward things that we learn, okay? And they both demonstrate KVL and KCL. So this is setting us up here for, like I said, after this first exam, we are going to start looking at what, not that series and parallel circuits aren't real circuits, but, more complex networks where we have series and parallel branches, and so you have to be on your game. You're constantly interchanging between KVL and KCL and Ohm's law, and resistance. We're going to learn how to do parallel resistors today. Okay, so you need to be able to sort of weave and have all of that in your back pocket. So first thing I want to talk about is KCL, but I'm not gonna harp on this slide for a second. I'm actually going to go down and just talk about parallel circuits, okay, as we see here. All right, I like this one. I skipped one too fast. There we go. Okay, so the total current in the circuit is supplied by the source, okay? So you have, out of this source, there's a total circuit current that gets drawn, okay? As soon as it encounters the first junction, and when I say junction, I'm talking about something that has at least 3 terminals attached to it, okay? If it only has 2, then I just stick with the more generic node, which this is still a node, but I would call this a junction because, that's just my own personal definition. So when you hear me say that, that's what I'm talking about. So when you have a junction here of 3 terminals, now the current can go this way or this way, okay? Now I realize these arrows are backwards. I don't know I don't know why they're all pointing up, but they should be pointing down, because as you can see, as you take part of that total current down this first branch, you're left with the other 2. Do you see that here? I2 plus I3. So this is 2 and this is 3. So you have I1 plus I2 plus I3. So you take I1 away from that, now you're left with I2 and I3 up here, okay? Now you come to the next node. Part of it gets drawn down through R2, and so I2 plus I3 minus I2 is going to leave you with I3. Okay. Now here's what happens on the way back, right? Because you have to remember this arrow's backwards right here where my cursor is. If you go down here and you've got this other one coming back around, they add together again. So if you were to put an ammeter up here, or if you put it down here, it would read identical. If you put an ammeter here, or on the other side of that resistor, it would read identical. But those two values would be different, okay? You can even put it, if you put an ammeter right here, after everything is combined back together, you'll get the total current again. So it splits apart to each branch, and then it combines back together to come up to the negative terminal, which is usually where ground is. So all of that eventually makes its way to ground. Okay? Any questions on that so far? All right. So that's the idea behind it. And we'll show this in our examples that we do on the board. Okay? So they're exploiting something called KCL, or Kirchhoff's current law. So it's the same thing. Conservation of matter. No electrons created or destroyed. So if they go into a branch, then there has to be, both branches have to add up to what the total was coming into it. Okay? I'm actually going to write it a little bit different than this. So you may want to wait to take notes until I switch over to my camera view here. Okay? But that's the idea, is that the currents that come into the node equals the currents leaving the node. All right? It doesn't matter how many branches you have coming in and how many coming out, just like with series circuits. It doesn't matter how many components you have in series. It's true for all of them. Okay? The voltage rises equal the voltage falls, or the voltage rises minus the falls equals 0. Right? That's essentially what we're saying here. But I'm going to restate that on the board. Okay? So I think I'm going to go ahead and, let's see here. I just want to point something out. So we talked about last time how if you have series sources, in other words, if you took two AA batteries and stacked them one on top of each other, positive to negative, you would have a total of 3 volts out. So you have a higher voltage that's available to you. Okay? If you put voltage sources in parallel, you have the same voltage out. So if you put two AA batteries in parallel with each other, the total voltage between the two of them is still going to be 1.5 volts, but now you've increased your total capacity for charge, which means you have more total current available. So that's the trade-off. If you start looking into alternative energy systems like solar and wind and people putting this stuff on their houses, more than likely they have a combination of batteries that they've wired in series and batteries that they've wired in parallel. And so some devices they hook into the parallel source because they need higher current, and then for everything else they use the DC sources in series. Okay, so it's a pretty interesting, there's a lot more to it than just putting a solar panel on your roof. If you wanted to go off the grid completely, you have to essentially go through all of your stuff, see what all your electronic devices are capable of drawing at any one time if they're plugged in and being used, and you have to add all of that power demand up, and then you have to create a series of add in some extra capacity just in case you buy more stuff that might get plugged in, but you have to buy enough capacity for high voltages and also large current draws, and sometimes a mixed system of the two. So it's a pretty interesting endeavor if you ever decide to do something like that. But like it says, while the total voltage remains the same, the current increases by the amount of each source. So you have twice as much stuff to draw through. Just think about, the difference between a D battery and a C battery and a AA, right? The only difference is their size, their ability to handle, the ability to carry electrons, okay? But they all have the same voltage out. It's just that the D battery, you can get a lot bigger current out of it, and you can use it for longer because it's got more in reserve there that it can store. So that goes back to charge, capacity with coulombs, how many electrons. There's a higher coulomb count in the D battery versus the versus the C battery, obviously, right? Because there's more electrons. And coulombs are just a count of electrons. It's 6.25 times 10 to the 18th of them, okay? So I think, just sort of scrolling through here, I'm going to go ahead and head back over to the board, okay? All right. And okay, so let's try a basic one out here. So KCL, I would say, is the summation of the currents into a node minus the summation of the currents out of the node equals 0. And then obviously the other way to restate that is the currents in equals the currents out, the summation of them. Okay? So that being said, let's go ahead and do one, just the simplest parallel circuit that we can get. Just a DC source. One in parallel, another in parallel. Let's go ahead and work with some nice numbers just to start off with. 500 ohms and 1 kilo ohm, and let's make this a 10-volt source. Okay. And I'll restate this again. I don't draw. Some professors you'll see do this, like some professors on YouTube, and if you have other professors, even at Ivy Tech or somewhere else that you go, they'll put the ground in here. It's always implied with me that it's on the negative terminal here of the battery, unless I do differently. So that's my default. Okay. You'll see that in Multisim that's not good enough though, because they force you to put a ground in before it'll even run. Okay, or it'll run and it'll give you wacky answers because it won't have a ground reference to measure everything against. Okay, so much like the first step in a series circuit, okay, we're going to want to find the total resistance because that will then allow us to have the total current. Okay. So to find the total resistance, and this is in parallel circuits, strictly parallel. By strictly, I mean that there are no series branches anywhere. It's just parallel branches. Okay, strictly parallel. All right. It's generically found like this. 1 over R1 plus 1 over R2 plus ... plus 1 over R sub n. However many of them you have in parallel, add the inverse of each one together, take that whole quantity to the -1 because really it's set up to where 1 over RT equals 1 over R1 plus like that, okay? But if you take the inverse of each side, you get RT here, and that equals this. So that's, your book will show it a little bit differently. It shows you the derivation, okay? Now, this is for, this will always work for all resistor combinations. Parallel combinations, I should say. In other words, it doesn't matter if you have 2 of them or if you have 2,000 of them. This formula will work every single time, okay? Now, the book, and even in the PowerPoint, which is why I didn't point it out, there is another way to do it a pair at a time where you don't have to use an exponent. And it looks something like that. Here's the problem. If you start having 3, 4, 5, 6, you have to do this pair, and then you have to do this pair, and then you have to do this pair. So it's a pairwise combination that you have to do over and over and over. So it's inefficient to me if you have any more than 2. But, if you have to think about which one to use, just use this one because it'll never fail, okay? and it's not that big a deal. You find out where your -1 key, or some of you have a 1 over x key on your calculator. That is the same thing as, that. Okay, so add it all together, equals, take it to the -1. Or some of you are able to type it in as a caret, right, around parentheses, something like that. Okay, so this is for all resistor combinations. I will not use the pairwise calculations in any of my work, but I will use this one exclusively, okay? So that being said, I'm going to go ahead and erase that. So, in this case, I've just got 2 of them. So I'm going to go ahead and write this out like this. RT equals 1 over 500 plus 1 over 1K to the -1. Okay? So go ahead and punch that into your calculator. So, you're going to have to get good with your parentheses. You're going to have to get good with your exponents. And, how do you enter a fraction in? Okay? So go ahead and see if you can punch this into your calculator. Per Steve, I'm going to try to slow down just a little bit. My brain always thinks it's in a race, and so, like I was saying earlier, I get caught up and I just go. And when I don't have students in front of me, I don't have anything to gauge it off of. So in my head, nobody's stopping me, and so I just keep trucking. Okay, I'm going to go ahead and punch this into my calculator too. And I'm actually going to put, I don't know if I'll be able to do that or not. How about this? So 1 divided by, I have open parentheses, 1 divided by 500 plus 1 divided by 1E3, end parentheses, caret to the -1. Okay? So I don't know if you can see that or not. Probably not. It's probably a bad idea. Okay. And I get 333. Let's go see what the chat says. Oh, and Justin says, I'm building an off-grid solar camper for my residency in San Francisco to help dodge the high cost of rent. That's a great idea. That is a great idea. So I'm typing in the chat 333 ohms. There we go. All right. Okay. Well, now that we have that, essentially we can look at this. I'm going to erase this in a second, but we can look at this like this. Like this. We just took that combination from here to here, right? And we came up with a single resistance in its place. And so you could look at this if you just want to look at the totality of the circuit. That's essentially what we're dealing with here, okay? And so it's pretty easy to see. Once you find the total resistance here, then all you need to do is use Ohm's law to find the total circuit current. So same thing, VT over RT. Right? So this is going to be 10 volts divided by the total resistance of 333 ohms. What do you get? So Jordan asks, how many of the prefixes do we need to have memorized? Well, it says, for example, the book goes from exa to atto. You only need to know, I would say, giga through pico. So giga through pico. So 10 to the 9th through 10 to the negative 12th. Okay, so Nick got 30, and Steve got 30 amps, and Nick got 30 milliamps. Let me go ahead and punch it in my calculator here. So I've got 10 divided by 333 equals 30 milli is what I get. Okay. All right. Okay, now Steve says, yeah, 30 milliamps. Okay, so let's go ahead and figure out what each branch looks like. Okay, so one of the things that I would ask you, probably right after asking you a series question, is what's the voltage on the 500? What's the voltage on the 1K? What's the current through the 1K? And what's the current the 500 and then the 1K. All right. So, can anybody tell me what these first two are? So, what is the voltage on each resistor? Anybody? What is the voltage on each resistor? Hint, you don't need your calculator. Waiting for it to come up here in the comments. As I fill up my drink, sorry about that. $10 volts, 10 volts, 10 volts, 10 volts. Yes. So you are correct. So that's pretty easy, right? Kind of like when, with series circuits, if you know the current through one resistor, you've found all of them because it's the same. Okay, so these, obviously, this is directly connected to 10 volts. This is directly connected to 10 volts. So the voltage on the 500 is 10 volts. The voltage on the 1K, 10 volts. Very good. Okay. Now, using what we already know, and oh, hang on a second. I just lost my video. What happened to my video? Did it shut off? Sorry, my video just shut off, and it shouldn't have. I just put a fresh battery in. Sorry about this. Hang on a second. I don't know what happened here. Okay. Well, that was weird. Uh-oh. Okay, do I still have focus? I still have focus. Okay. Sheesh. I don't know what the deal is there. Okay. Looked up at my screen. It was blank. All right. So I was getting ready to say, using what we already know, okay, I'm going to find these two currents using nothing but Ohm's law, okay? So the current through the 500, just the voltage divided by the resistance, right? So that's 10 volts divided by 500 ohms. I felt like using this today. Feels so bulky compared to what I'm used to with my phone. 20 milliamps. Okay. And then the 1K, 10 volts divided by, 1K. All right, so something like this. What's 10 divided by 1? That's 10. What's volts divided by kilo ohms? Milliamps. Okay. So let's see if this shows up here. So we have a total of 30 milliamps. Down here through the 500 we have 20. And then over here we've got 10. Okay. Yes, John, correct. All right. You can see, with series circuits, we said that if they have a higher, because it's directly proportional, if they have a higher resistance value, they have a higher voltage drop, right? Well, with parallel circuits, you can see the lower the resistance value, meaning there's less effort to stop the current. If there's less resistance, you have more current because they're indirectly proportional, inversely proportional, inversely proportional. So you can see how it splits up there. 30 milliamps, and then half, 2/3 of it goes down 500, and then 10 of it goes down 1K. And you see that because 1K is twice the value of 500, it has half the current. Okay, there's a direct correlation there. That's why I specifically use these two values so you could see that, okay, easily. So double the resistance, half the current, okay? And so we could just keep adding stuff in parallel, adding more loads, and as long as the supply could handle it, the only thing that would change, those two branches won't change because those are still just 10 volts divided by 500, 10 volts divided by 1,000, okay? But the total current will change because you're drawing more total current from the source even though it's getting split up, okay? So that's the big difference between the two. All right, any questions? Let's go see. Yes, yeah, you got them backwards, John. That's okay, though. All right, well, let's keep going here. Make sure that's in super duper focus. All right. I'm going to write up in the corner here, so RT equals 3, 3, 3. I'm also going to remember that, well, I guess that'll be up there like you see here, okay? I'm going to go ahead and erase this, okay? So we did everything that we needed to do, and if we wanted to find the power dissipated by each one, same thing, would be 10 volts times 20 milliamps. So this one would dissipate 200 milliwatts, okay? This one would dissipate, so 10 milliamps times 10 volts, that would be 100 milliwatts. So 200 milliwatts and 100 milliwatts, okay? So both of them are under a quarter. So let's see here. So that's one way to do it, okay? The other way to do it is with current division. So much like we had voltage division, we also have current division, okay? And generically, that says the following. Any individual branch current is equal to the total current times that same ratio we had last time inverted. So now it's RT over the individual resistance. Okay? So, that's something that's going to be a confusing thing that you need to make notes about, okay? And when we're using current division, it's always total over individual, and you'll see why when we do the calculations. And with voltage division, it is the individual resistance over the total, okay? Because if you did it the other way around here, you'll notice that, we did 1,000 and 500, okay? One of the things about parallel circuits is that the total circuit resistance is always going to be less than the smallest resistor. Okay, I didn't mention that, but that's the first check that you should have. Okay, so when you do your parallel combination, is this number smaller than your smallest resistor? Okay, so if you put the individual over the total for this, you're going to get something that's greater than 1. So you're going to end up with something that's greater than 30 milliamps. So it's reversed on this side, okay? Same thing with the voltage. You add those all together. So if you had it reversed for that one, the total would always be bigger, and you'd end up with something that was greater than the total, because that coefficient there would be 1, okay? So that's the general format of it, okay? So the individual current, branch current, is equal to the total being drawn from the source times the ratio of the total to the individual. Okay, and this works for every parallel combination. Okay, so I'm going to go ahead and erase this, and I'm actually going to do it. And we'll see if we come up with the same answers here. So the current for the 500 is equal to 30 milliamps, because we already found that, so you have to have that information first. And then times the total, which was 333, over this individual branch, which is 500. Okay, go ahead and punch that in. So again, this is current division. We're using the ratio of the total parallel combination, however many resistors those are, to each individual resistance. Okay. Giving you time here to punch it all in. Like I said, this is rough for me because I got no feedback. So 30 times 333 divided by 500. Ooh, that one rounds up to a nice number. That looks good. Okay, well, I get 19.98, which rounds up to 20 milliamps. And I guess more specifically, since we are rounding it up, we should say 20.0 milliamps. Okay? So that checks out. Just for fun, let's make sure this one works too. So here we've got 30 milliamps, and you can see just by the presentation of the two equations here, obviously this one is twice as this one, right? Because this one is, you could look at that as 500 times 2, and so you're taking half of whatever this was. But anyway, all right, there's the equation. And so mine actually turns out to be 9.99 milliamps. Okay, now obviously if we round that up, that is 10. So it looks like we did it correctly, right? So somebody asked last time, I think, like, what if we get this answer, but the answer should be 10, but we put this one in, right? So remember I have tolerances like plus or minus 0.05. So I would accept up to like 10.05 and all the way down to 9.95, right? I would do it a couple different ways and then see how you may or may not round up, and then that's how I generate a tolerance. Okay? Any questions on that? I think we should up the ante here. And, yep, no questions so far. So, yeah, let's keep going. Let's do another one. And this time we're not going to use nice numbers. Okay. All right. Well, let's go with. Whoa, I just about did chapter 7 on you. Ha ha. Jumped ahead. That's no good. Okay. That would have been fun. Especially if I wouldn't have checked the chat and you went into panic mode. I'm just kidding. It's not that bad. I shouldn't say that. Probably stigmatizes the second third of the class, but I just want you to be prepared for it. I want you to put in the right amount of time. All right. So there we go. So we got now 3 resistors, and I love to use my favorite trio of 2.2K, 3.3K, and 4.7K. Those are my favorite standards for years, just because I saw so many of them when I was a student. And let's go with, it's okay if we have small currents on this one. How about just 5 volts? Okay. So for this one, I'm going to let you work ahead a little bit here. And so again, I would start off with this. Then I would find this. And certainly, you could just right now, without doing this or this, you could say 5 volts divided by this. That's this current. 5 volts divided by this. That's that current. 5 volts divided by this. That's that current. Okay? I realize that you can do that. But I would like you to start getting in the habit of using the current division, because it's going to be important when we go to the chapter 7, 8, and 9. Okay? So just get in the habit of always doing it that way. Double check yourself with Ohm's law if you want to. But get your technique on current division down. Okay. So start there, and then I'll jump in. Go ahead and write the equation here. See if you're on the right track. To the negative 1. Okay, so I see an answer of 1.03 kilo ohm And that's what I got. Okay. And again, I just punched this all into my calculator and let it do the work for me. If I would have used the pairwise, I would have had to do these two first, gotten an equivalent, and then taken that value and pair with this one. Okay, you have to keep doing it over and over and over, and I don't like doing that. This you just let your make sure that you know how to use your calculator, and if you can do this, it saves you so much time in these calculations. Okay. All right. Well, let me go ahead and then find the total current here. So I've got 5 volts divided by 1.03 kilo ohms. Oh, man. Divided by 1.03. So 4.85 milliamps. That's the total. Okay? And so now we know it's going to go here, here, and here. Okay? All right. Well, now my next 3 questions are obviously going to be, what is the current through the 2.2K? What is the current through the 3.3K? What is the current through the 4.7K? How's that all split up? Okay. So our total is 4.85 milliamps. Okay, so I'm going to set up the first equation here, and I'm going to put this so that we have this separated. So 2.2K. So that's going to be 4.85, because that's what total comes into the node here. Okay, milliamps. And times, that's going to be the total of 1.03 kilo ohms over 2.2 kilo ohms. Okay, that's the first calculation. Did you get 2.27 milliamps? Okay. So that's how much this pulls, 2.27 milliamps. Now, just like I talked about before, because this is the smallest resistor, right? I didn't check this again, but I just wanted to point this out, that 1.03K is less than the smallest resistor. You'll also notice that this should be, and we're going to watch for this, this should be the highest value current of the 3 because it's the smallest resistance, right? V equals I times R. If this goes down, that goes up. Okay. So let's look at the next one now. So this is now, again, 4.85 milliamps, and we are using current division here. I realize you could use Ohm's law, but I want you to get in the habit. 1.03K, the total over the individual, which is 3.3K. Should be a little bit smaller. 2.2 is roughly, 2/3-ish. I get 1.51 milliamps. So 1.51 milliamps. Milliamps. Okay. Very good. Ben and Steve. 4.85 and 1.03K. And now this one is the 4.7K. Go ahead and find that last one. Okay, so Steve, okay, we're starting to get some answers here. 1.06 milliamps, that is correct. All right. Okay. Now, just like we had a check with KVL, where we added all the voltages together and they have to add up to the total source voltage, we're going to add up all the currents individually and see if they add up to the total source current. So I've got 2.27 plus 1.51 plus 1.06 milliamps gives me 4.84. So I'm off by a hundredth. Okay. So looks like we did it correctly. Is there any questions on this? You guys are keeping up good, and you guys are all getting good answers here. I love it. Okay. See, you should you know, the notes that you're taking on this, if they're well organized, you should take a picture of it and go, oh man, look at this. Man, I had a rough day. Or maybe you should wait until we do series parallel. Those are better. Where you sometimes you take a whole page. Any questions? All right, we're going to do one more, and you're going to do it on your own, at least for a minute. I want you to set it all up, and then I'll come in behind like I just did. So go ahead and start working through it. This time I'm going to do 4, and after that, I'm going to go over to Multisim, plug that 4 resistor parallel circuit into it, and then we're going to talk about Multisim from there on out, okay? So get this erased here. And again, if you wanted to check yourself to see if you got the right currents, you could have used Ohm's law just to double check yourself until you feel comfortable with your, I don't check them anymore because I'm confident in my current division technique and my calculations. So, all right, so let's take it up one more notch. And let's work with some big currents this time. How about let's just stick with 100 ohms, or 100 volts, I'm sorry, 100 volt source, and 175 ohms, 470 ohms. Let me write them on the other side here. 175 ohms, 470. Let's do 225 and 600. Okay? 175, 470, 225, 600 with a 100 volt source. Okay? All right, go ahead. So again, 175, 470, 225, 600 ohms. So there's how I would set up my equation for that. Okay, getting some answers of 71.7 ohms. And that is what I have gotten. And does that make sense? How much did we say? We said 71.7. 71.7 is lower than the lowest resistor here. Okay? So, maybe we all punched it in the wrong way, the same way, but I doubt it. So I think that's probably correct. So 71.7 ohms. It's not very much. And then we have a 100-volt source and a 71.7 ohm total resistance. Whew. 1.39 amps, whole amps. That is a pretty good draw there. But what do you expect with a 100-volt source and everything's under 1K, right? So we have a total source current of 1.39 amps. And if you guys want to, even if you just have a pen and a pencil, at least that gives you two colors to, if it's all in the same color and it's all smashed onto the same circuit, sometimes it's hard to read. But if you have a different color, or if you use colored pencils or colored pens, it's nice to have that distinction when you go back and look at it later, instead of just trying to make sense of the mess. Okay, so I try. That's why I always buy the color packs. And this one's only good for stuff like this. It's too light for everything else. So, okay. So now, obviously, the question is going to be, what are the individual branch currents? Okay. We start with the current through the 175. Yeah, John says, oops, I put a 7 on accident. Should be good now. Okay, so if I was going to do current division for this, I would start with the total current times the ratio of the total resistance, which was 71.7, to the individual resistance of 175. And because this is the small one, I expect that this will have the largest current. It's nice to hear the buttons again. Up. Did it auto shut off again? You son of a gun. Well, I'm going to have to get into the settings later and figure that out because that is unacceptable. Okay. All right. Well, before my camera interrupted me, I was getting ready to put down. What was I getting ready to put down here? Oh, I messed it all up, didn't I? Here. Times. I get 570 milliamps. Is that what you got? So, holy smokes, we got. Oh, you did them all. Okay. I was like, wow, we've got a lot of different answers, but you're doing them all. Okay. So, yes, I get 500 and I'm going to call it 570 because I actually get 569.5, and I'm going to round that up to 570. So, 570 milliamps. It's pretty good. 570 milliamps. Okay. On to the next one. So now this one is the 470. I'm just going to go left to right. And the answers are in the comments. Steve has left them in numerical order. If you want to check yours against his. I don't know if his are right yet. First one was. And so now this is 470 underneath here. Ohms. So 1.39 times 71.7 divided by 470. I get 212 milliamps. Mercy. 212. So that comes through here. So 212 milliamps. Cool. All right, now we're going to go to the next one. And what I'm going to do is, whoops, I'm going to erase this part. And now the current through the 225 equals 39 times 71.7 over 225. $443 milliamps. So this one is 443 milliamps. And then we have the last one, the 600, which should be the smallest. 1.39 times 71.7 over 600 ohms, and 1.39 times 71.7 divided by 600, and we get 166 milliamps. Now, does that make sense? I'm going to add all these together. So I got 570 milliamps plus 212 milliamps plus 443 milliamps plus 166 milliamps. That gives me 1.39 amps. Very good. Very, very good. Okay. So John asks, are these answers based on significant figures? Yes, I'm always using 3 significant figures. So I'm always going to round up to the third least significant bit, essentially. Bit. That's not this class. The third significant digit. The third least most significant digit. The first 3, the most significant and the 2 after. Let's put it that way. Okay? And always in engineering notation. So that's why you see here, like some of the answers here, like 71.7, that's 3 significant figures. And 1.39, and 569. So even though they're not, 1 or in the hundreds or in the tens, it's always 3 sig figs. Says yes, 570 is only 2, but we rounded that up from 569.5. So we had more resolution available, and then we rounded up to 570, and that zero, the trailing zero, then becomes a significant, okay? Because 569.5 is 570, right? And that's what the rules of rounding up tell us to do. So, yeah. All right. Well, now I'm going to put this same program into something called Multisim Live, and I will suggest that if you're going to look at this and try to do this yourself, that you have a Chrome browser. All right. I do 95% of everything I do in Firefox. That's what I've used for, 15 years. That's what I'm comfortable with. I don't like using the other ones. However, this Multisim Live and even the Every Circuit, this stuff is designed to work inside of Chrome better, okay? So I always go over to Chrome for all that stuff, any of my online circuit simulators, okay? So I'm actually going to go into my OBS here, and I'm going to pull up my Chrome, all right? And I already have a login for here. Well, let me get it. See, I'm so used to doing this, I went right back to Firefox. I already have. There's something else called Every Circuit, which I may do a little video on at some point. That's what I did my master's directed project on, instead of doing a thesis. Was incorporating apps, circuit simulation apps, into the classroom. Okay, so I probably will do a little video on this. But here's the thing: is now Multisim has joined the game, and for everything that we do, you might as well just use Multisim Live, because if you are to take other classes at some point face-to-face, if you are EET, then you're going to be using the full version of Multisim anyway, but they're all pretty similar, and there's probably other online circuit simulators as well that are getting better, but Multisim is sort of the standard. So if you want to get there, if I'm going to type in, I say Multisim Live. Okay. It says Multisim Live Online Circuit Simulator. Okay. So you want to sign up for free. Okay. Well, let's see. Online. Yeah. So you can hit this little button up there in the right-hand corner where it says sign up. Okay. And so you just create a username and password. That's all it asks you for. All right. Now this is going to be important when I have you do, I believe you're allowed to save your circuits if you have a login and password. If not, you can only go in and just use it to get answers, okay? Now, to do that, if you I think you should go ahead and create a username and password, but if we go back here, underneath, you see here it says Online Simulator. If you just go straight to the Online Simulator, okay, it's got some default thing that it comes up with here. And then you can go ahead and open it and delete what you see there, and then just start off this person's profile, okay? And so, for whatever reason, when I search for Multisim, the online simulator, this is the one that comes up. And so somebody else wrote this one, but you could just go ahead and open the circuit. Say, yeah, open anyway. And it initiates it. As we're working. My computer doesn't like that I'm trying to do more than one thing at once. Even though it's an i7, it doesn't act like it is. So there you go. So, it comes up in this split right here. And so you could do like a Control A and then just delete it. Okay, and then you could go ahead and go from here. However, I would prefer that you, yes, I want to leave the site. I would prefer that you go into your profile. That way you can create these things and you can also save them. So I'm going to go ahead and log in here. And my password should be saved. Okay. Thank you for all that. Sure, whatever. There we go. And log in. Okay. Now I already have some of these created, and if you find my profile on here, which is, you can see right there in the address, multisim.com contributors /217827 Professor John EET. Okay, and I don't know if you can like follow people on here, or I don't think there's friends or anything. You could, I think you might be able to favorite somebody's circuit, and then you can come back to it. But anyway, I'm going to go ahead and create a circuit up here on the right. So Steve asks, is Multisim Live the same as every circuit? No. No. And I don't use Twitch anymore, and I don't use Discord. I used to watch a woodworker on Twitch who then switched over to YouTube, so I had no use for Twitch anymore. And then Discord, I used to play Star Wars Galaxy of Heroes for 3.5 years. My goodness, did that turn into a job. Never again will I play any RPG. Is it RPG? No, it's RNG, random number generator games, where you're just basically playing casino, type stuff, and you always have to buy the new meta, and just, I can't believe I got sucked into that. It really, really bothers me. So that's just an aside here, all right? Anyway, so here we go. So I just want to go ahead and point out, yours may not come up like mine did. You may come up with the split, and that's just a different way to look at this stuff, okay? The schematic is where you enter your circuit in. The grapher will tell you what's happening over time. This is kind of like an oscilloscope. And then you can also have a split view where you have both of them at the same time. So I'm just going to stick in the schematic view, okay? So I'm going to quickly look back at our work. So we had a 100-volt source. We had 175 ohm, 470, 225, 600. Okay, we're going to go ahead and put that into Multisim Live here. So over here on the left, I don't believe in my OBS it's going to, well, it might. Let me see. Let me pull this down real quick and see if I can see it. Nope. So it's not showing you. As I hover my cursor over these, I'll just tell you what they say, and then when you hover your cursor, you can actually see the little pop-up window. But that says analysis and annotation. Those are your probes. The next one says schematic connectors. The next one says sources. The next one says passive. And then you get into stuff like analog. The next one's diodes, transistors, indicators, switches, modeling blocks. I mean, there's all kinds of stuff that's here, all right? So the first thing I'm going to add is my source. That's typically what I always do. And so that's this one right here. Okay, so I click on the source. And when I do that, okay, so you can see that menu. So I'm going to go ahead and add the DC voltage. And if you are in my, if you're in my 112 class, you see that there's also, if you click on this, there is clock voltage. So that's like you could do a digital circuit here. And there's also there are gates that you could use. So, but I'm working on the Quartus install. I just got the install video down, and so the first program video will be there shortly. So there's my first source, and I'm just going to leave it at 12 volts, just the default value. I just want to get my components on there, get them aligned, get them in the right spot, make all the connections, and then I'll go and mess with the values of each one. So I'm not concerned about what value of a component I'm adding, because I can easily change it, and you'll see that. So the next thing I'm going to do is I'm going to add my 4 resistors. So that's under passive, and so I want a resistor here. Now this is what's neat about the way you plug this into here. So as soon as I click, Okay, I've got these 4 options here. This one says, oh no, I don't want to delete it. I didn't mean to do that. This one will rotate it, which is what I want to do. That's one of the things I want to do. And the other thing is duplicate, and that's this little copy. That's the symbol for copy, right? Or duplicate. And so I want to do that. 1, 2. You don't have to do this. You can go grab it from the passive menu every time, but they do this so you can quickly add components. So there we go. So there's 4 resistors. Okay. Now I need to come over here and I need to grab a ground. So that's over in the schematic connectors, and there you see I've got a ground. And so all Multisim projects have to have a ground on there. All right. Now I'm going to better align this because it's bothering me. And okay, those all look good now. All right. So if I want to make, notice how I have the great big hand there, but then if I hover over the little point, now it looks like a little spool of wire where I'm going to come all the way down here because I always do the outside first. And I click when I want to make a right turn, and then I connect. So it was click, turn, click, down. Okay, left click. And then I'm going to do the same thing down here. Click, turn, and pull, and then click, turn, click, and make the connection. Now I just need to make these internal ones. So I can go from click, click, left click, left click, left click, left click. Okay, I'll stop saying left click. Click. All right, now I'm going to go ahead and attach my ground, and I just select it, move it up until it makes a connection, and you'll see when it does. Whoops. Come with me. There we go. So I've got my finger held down on the left mouse button, and you see that it's showing me I don't have a connection out here, but when I make a connection with the wire, it alerts me by those concentric circles there. Okay? So there we go. Now, this bothers me because I like everything to be straight. Oh, okay, I'm just going to have to delete that. So if you want to delete the wire, select it, and then you can delete it. I like everything to be nice and straight. Okay, that's much better. All right. So now I need to change the individual values here. So this very first source here was 100 volts. So I double click, sorry, I just did that without telling you what I'm doing. So I'm going to double click the value, this 12 volts. I double click that and it brings up this menu, and it's got a slider and everything. I don't try to pull it and do it like that. I actually come up here and type in 100, enter, and then I click out of it. So there we go, there's 100 volts. Okay. Same thing for this one. I'm going to click on the actual value. This one was 175 ohms. Now notice, if you need to do a prefix, lowercase k is kilo, uppercase m, so if I did 1 meg, okay, that would be 1 meg. If I do a lowercase m, 1 lowercase m, that would be 1 milliohm. That's a really tiny ohm. Okay, and then if you want to do gig, right, 1 gigaohm. If you wanted to do 1 micro ohm, you just use a U, okay, and then it goes ahead and puts the mu character in there. So that's not what I want. I want 175. Just showing you that if you need to use a prefix, that's how it's done. Okay, and then this one was, oh, if we look back here, that was 470. And then the next one, double click on the value, and this one was, whoops, that one was 225. Not 225 like that. There we go. And then finally we had a 600. Whoa. 600. All right. So There we go. I'm actually going to make this screen a little bigger here. OBS, you're wonderful. Okay. So, I actually want to pull this to the side a little bit more. Fill out the screen. All right. Now, if I were to go ahead and hit the play button on here and run this, actually, let me go check and see if we've got any questions so far. Okay. If I just went ahead and ran this, and I'll go ahead and do that. Let me go ahead and run it. Simulator loading. Okay. So it's running right now. You can see the elapsed time up here, but this is just like turning something on. Now, we could put some indicators in there that show us which branches are on and which ones are off. Okay. But we want to go ahead and put probes in here that will allow us to do measurements, because right now this isn't telling us anything. Even if I go over here to the grapher, okay, I don't have any probes set up, and so I can't graph any data. Okay, so I'm going to go ahead and stop this, hit the stop button, and you see my menu comes back to me. And so I want to come up here to the very, very top one where it says Analysis and Annotation if you hover your mouse over it. And I want to do a current. I'm going to put a current probe in, and you can tell where you're allowed to put it. Same thing, it'll do those concentric circles. So this is going to be my total current out of the source. Okay, and yes, that's correct. Okay, so that's going to give me my total out of the source. And then I also want to do each individual branch. Now, I already know what the voltage is going to be across each one. It's going to be 100 volts across each one. So I'm not really worried about voltage in this case. But I do want to put in a few more ammeters. So I'm going to grab a current. And there we go. I'm going to measure that branch. Now, you may be asking yourself, well, hey, that's pretty easy. I don't have to break the circuit. And you are right. You're not in danger of blowing anything up, and so they allow you to cheat on here. When I show you how to do Multisim, and I will, I'll show you how to use the full version. They do have these probes in there, but I also show you how to use the actual equipment. And if you're going to use a DMM, it's not there is no DMM here as far as I know. But if you use a DMM, you have to use it like you would use it in real life. Okay, but this sort of lets you. I don't want to say cheat because that's not fair. It's more advanced because it knows what you want to do, and you just want to get the answer quickly. And so here's what they do. So here we're going to get the total current, and then we're going to get each individual current. So we go ahead and hit the play button. So there you can see they actually got if we round that up, that's 1.40 amps, which is okay, that's fine. And then they got just a little bit higher, 571. Got a little bit higher here, 213. A little bit higher here, 444, and then 167. So everything was about a milliamp higher. Not a problem, okay? Because when I say milliamp here, we're talking about 500. So the milliamp place, in this case, is the least significant bit of a 3 significant figure value, okay? So I'm not worried about a milliamp here and there in this particular case. Okay? Any questions? So there you go. All that work that we did on the board, Multisim did at the drop of a hat. But, again, this is your best study tool that you're going to have all summer long, because you can come up with whatever crazy circuit that you want, and this will analyze it every single time, and it'll give you the right answer. And it's your study sessions are only limited by how much patience and discipline you have, because obviously it's operational 24 hours a day, so you can just keep doing these over and over and over until you just get sick of them. And I guarantee you the rest of the class will make more sense if you do that, especially for this first exam. Okay? So any questions? So Nick says, why is it measured before the resistor? Oh, okay. I can address that. I'm going to go ahead and hit stop here. Okay? So he's saying, why are you measuring it before the resistor? I could measure it after the resistor too. Okay? And if I go ahead and hit play, you can see it gives you the same current, because the branch current here, this current right here on this side of the node is the same as this. Before you get to the junction on each end, it doesn't matter if you're in front of or behind the resistor, it's the same branch current, okay? Now, let me throw a caveat in there and talk about, because we haven't really addressed this part of it yet, but if I were to put an ammeter in, let's see here. Okay. If I put an ammeter here, it is not going to read any of these. It's going to take the 1.39 minus what was drawn off on this first branch, and that's how much we're left with. Now, this is not a calculation that we did, but I'm just showing you, where you place the ammeter absolutely matters, okay? If it's on, I don't know if it'll, no, well, let me do it while it's running. So if it's on a branch, it doesn't matter if it's behind or in front, okay? And so you can see there, so 1.39 amps minus 571 milli leaves us with 823 milli, okay? Now, if I put another one in, now this next one up here, instead of pulling from 139, this is what was left over. So now this second branch is going to draw down 213 out of that 823, and it's going to leave me with something else. Okay, so there you go. So 823 minus the 212 leaves me with 611 up here, and then that gets split into 444 and 167. Okay, so that's the complete picture of this whole circuit. Okay, everybody see that? And again, these two, it wouldn't matter if I put it here or here. This far probe on the right, I could put it up here. So in other words, if I move these bubbles out of the way, and it's not going to let me do it. Can I do a control move? Nope. Okay. All right. Well, I can move the whole thing, and so I could move this down here. Whoops. Can I have this one? And I want to move it down all the way down here. Whoops. Can I have my circles? Okay, now that is pointing backwards. And so, can everybody see that? I don't know if I can I zoom in here? Oh, yeah, perfect. Can you see that this arrow is pointing the wrong way? So when I go to do this one, it should read a negative number because the probe leads are backwards. So you can see there it's negative. So if I need to change the direction, you have to select it, and then you see over on the right-hand side, there's this option that says flip current measurement. Click that, and then it'll put it back the right way. And then it will read properly. Okay? Okay, so Nick, if you were measuring the voltage on each side of that resistor, that's a different story. You have a different voltage potential before the resistor and after the resistor, but the current through that branch before the resistor and after the resistor, the current remains the same. Okay? Just think about a series circuit, right? What happens in between resistors in a series circuit? It's not like the current drops after it hits the first resistor and then it drops after it hits the second resistor. That is the staircase of voltage, right? The voltage rise and then the voltage falls. But with these parallel circuits, each branch is consistent. So let me illustrate and just let you peek into Chapter 7 for a moment. Let's say, and by the way, this is not going to be on the exam or any quiz anytime soon, okay? And this thing wants to keep testing my sanity. It really does. There we go. Oh, it is the battery this time. Okay, so let me see if I can get this in here real quick before I switch back over. If I had 1, 2, 3, 4. If I had 3 resistors, the way that I would find the total resistance here is because they're on the same branch, I would add them all together. But if I measured the current here, or here, or here, or here, those would be an identical measurement because they're on the same branch, okay? So whether you're measuring up here or down here, that is one single current, okay? So hopefully that clears that up before this thing. Oh yeah, I wonder if it's blinking it through on the. Oh, it is. It's blinking it through. It's blinking it through to YouTube, the little battery. Okay. All right. Well, this capture card must demand more of it since I'm doing 1080, because that didn't last very long at all. It's not even 3 o'clock yet. Okay. Any questions? Okay, well, let me come back to the Multisim real quick. And so now let's say, okay, I went ahead and solved that one. And so now I want to do a series circuit. Okay, so how would I deal with all of this? I probably would do just select and get rid of. Select this thing, hit the X, select, hit the X, and do that for all of these. And I'm holding down the control key and doing them all at the same time. Okay? And I really want to get rid of that and that and that and that because I want the resistors by themselves. So I hold control down and select all of that. And then hit the X, same thing down here. I'm going to select all this. And I don't want I don't want that to go, but it may get deleted here. That's fine though. I can nope, it didn't. Okay. So now I'm going to take this up here and I'm going to rotate it like that. Take this one over here. Take this one down here and then rotate that one. And have something that looks like this. And so now I'm going to make a series circuit and just do a couple little measurements here. So you can see me using the voltmeter. That's going to go up here. Okay. And just for ease, I'm going to make this 400. No, I'm not. I'm going to make it 100. Let's just make it 100. And let's make this one 150. Or no, how about 125? And then this one is, what, 175? Is that total? No, 275. My goal here is that I want them all to add up to 1K. So 700 plus 300. Oh, that's I've got too much. So this should be 175. Just because it's going to give us 100 volts divided by 1K. All right. So now I'm going to go ahead and put my ammeter in. I'm going to put one in here. And I want that flipped because I want it pointed the right way. And then I'm going to put another one in right over here. And then I'm going to put another one in down here. And that one needs to be flipped too. It needs to go the right way. All right. Now I got my series circuit set up. series circuit setup. There's 300 plus 700 gives me 1K. So I'm going to go ahead and simulate this. Uh-oh. Holy smokes, I didn't get the... I think it went ahead and did it anyway. Okay, so see, no ground node was found. It gave an error. I understand. I'm sorry. Will you simulate it now? It still gave the right answer. Okay, there we go. So no matter where I measure in this series circuit, the current is exactly the same. So here's where things get different. I want to know, I'm going to get rid of this because these are just going to take up space. So we know that the current is 100 milliamps. Whoops, I want that. No. I want this to stay. All right, now I'm going to come over here to the voltage. Okay, so voltage, watch what happens. Wherever you place your first voltage probe, that's the red. Okay, so here is, I put it down. Now, one of my choices is add a reference probe. This is the black probe. I'm going to reference it on the other side. So I'm looking for what's the voltage drop across this resistor. So let me go ahead and simulate that. So there we go, 10 volts, which I would expect if I have 100 milliamps and 100 ohms. That's going to give me 10 volt drop, okay? So there you go. So that's if you wanted a, if you were trying to make a DMM measurement, like with your multimeter, okay? Let me show you another one. So now I'm going to take a voltage probe, and I'm just going to put one of them right here, okay? If you don't have a pair with it, it is always referenced to ground, okay? In other words, this is the node voltage if you just have one of them. And notice these are named two different things. So this is PR1, this is probe 1, positive, and then this one is the reference to 1, okay? This one is just 2 by itself, and you see that it's referenced to 0. So 100 volts at this node, you drop 10, and then you're left with 90. So this will do not only the node voltages all the way around, but it will also do the voltage drops. Okay, and so let me do this again. So let me do another voltage drop. Go from here, give me the negative, so I can measure that voltage drop. And then I want to come back up here, voltage. I'm going to go across this one. So there's one side. Here's the negative to that. So now I'm going to go ahead and simulate this. Okay. So there we have 10 volts. We have 12.5 volts. We have 17.5 volts. And then this 600 is going to take the majority, right? Because it's 6/10 of 100 is probably what it's going to be. So now, because this one's on the bottom, now notice how I have to do this voltage, and I did this intentionally. So I've got one probe on, that's the red, right? You always go high potential to low potential. Okay? So there you go. Okay? Now, this is kind of silly, but I'm going to go over to the graph review while this is running. And this is why we don't use oscilloscopes in DC, because it's all straight lines, and that's not very interesting to look at. Okay? Now, when we get to AC, then it becomes interesting because you can look at, the phase differences between different signals and all that good stuff. So, yeah. So, not very excited while we're in DC. When we're in DC, we just really want to know what these numbers are. Okay? Any questions on this? All right. Well, I'll tell you.